everyone, welcome to second video lecture series on module 3 probability distributions of 4th semester subject complex analysis, probability and statistical methods with subject code 18MAT41. In last video lecture we have taken random variable, discrete and continuous random variable. In this video series I am going to take binomial distribution and problems. In probability distributions, we are going to take 4 probability distributions, 2 each in discrete probability distributions and continuous probability distributions. Under discrete probability distributions, we take binomial distribution, Poisson distribution, and under continuous probability distribution, we are going to take exponential distribution and normal distribution. Before taking up the probability distribution, let us know the usage of probability distribution. The distribution function, both discrete and continuous, are widely used in simulation studies. Now, what is simulation studies? Simulation study uses a computer to simulate a real phenomenon or process as closely as possible. And this simulation study often eliminates the need of costly experiments and also often used to study problems where actual experimentation is impossible. Now, under discrete probability distribution, we are going to take two distributions, binomial and Poisson. The usage of binomial distribution, we can say a study involving testing the effectiveness of a new drug. The number of cured patients among all the patients who use such a drug approximately follows a binomial distribution. Now, Poisson distribution, operation of ticketing system in a busy public establishment, example airport, metros. The arrival of passengers can be simulated using Poisson distribution. Binomial distribution. Now consider a trial or random experiment which has only two possible outcomes. For example, tossing a coin. We can have either head or tail. Result of an examination. Passing the exam or fail in the exam. Manufacturing item, defective or non-defective. So this trial which has only two outcomes, we can call it as success and failure. Then the trial is known as Bernoulli trial or binomial trial. That means a trial with only two possible outcomes, say success and failure, is called a Bernoulli trial. And this trial is finite and each trial is independent. And the probability of success in each trial is fixed, a constant. Now for example, if you are randomly select a card from a deck of cards and note if the card is an ace, you then put the card back and repeat this process 4 more times. So here 4 trials we have taken. Each of 4 selection represents an independent trial. Correct? It is an independent trial as the card is replaced back before the next one is drawn. And what are the possible outcomes? There are only two possible outcomes. Either the card is an ace or not. So we are noting down whether the card drawn is an ace or not. So that means the two possible outcomes. If suppose the drawn card is an ace, we call it as a success. If not, then it is failure. And what about the probability of a success drawing an ace? Every trial that is fixed 4 out of 52. 4 by 52. Therefore, this is a binomial trial or Bernoulli trial. Now let me take one more example. If you roll a die 8 times and note down the die lands on. So this is not a binomial trial. Why? Although each trial is independent, there are more than two possible outcomes. So that means the sample space, it may roll out to 1, 2, 3, 4, 5, 6. So the possible outcomes are more than 2. So therefore this is not a Bernoulli trial. Now suppose if I say P is the probability of success, let P be the probability of success in each trial and Q be the probability of failure in each trial. So since there are only two possible outcomes, P plus Q must be equal to 1, totality of probability. Now if suppose we take Bernoulli trial n times, so n times we conduct a experiment, random experiment. The probability of X success out of n trial. So how to find the probability of X success out of n trial? So that is defined by P of X equal to NCX into P power X into Q power n minus X. So that means X probability of success P occurred x times, means definitely out of n, x is the success, means n minus x is the failure. So we have probability of x success means there are n minus x failure. So together it is P into x times q into n minus x times. So it is P power x q power n minus x, and it can be in any way, NCX ways. So that's why the probability of x success in n trial is P of x equal to NCX P power x q power n minus x. So this is the probability function of binomial or Bernoulli trial, and the collection x along with its probability function, that is x and NCX P power x q power n minus x, defined for each x totally is called binomial distribution. So that means binomial distribution is based on the total number of trial and the probability of success P. So if I know the total number of trial and the probability of success, then definitely I can find Q, that is 1 minus P. So I can calculate the probability of X success out of n trials. Next, mean, variance and standard deviation of the binomial distribution. So how we can compute mean, variance and sigma of the binomial distribution? Mean mu is equal to n into p, variance v is equal to npq, and standard deviation, that is square root of variance, so that's why it is root npq, where n is the total number of trial, p is probability of success, and q is probability of failure. So we use this to calculate mean, variance and sigma of a binomial distribution. So let me take one example for binomial distribution. Suppose I take 5 fair coins and observe the head turning up. That means the basic experiment, 5 fair coins are tossed. Event of interest is total number of heads. As all of you know that for each trial, the probability of success, that is head turning up, is equal to half, 1 by 2. And so the number of heads in the 5 coins is a binomial random variable with the total number of trial n is 5 and probability of success is 0.5, which is fixed. Now suppose if at all this experiment is carried for 50 times and one has observed the total number of heads. So that means out of 50 trials, so the heads 0, 1, 2, 3, 4, 5, observed fact, the observed frequency is 1, 11, 11, 19, 6, 2. So in each trial, out of 50 trial, this is the observed fact. Now if at all I want to fit it to binomial distribution, that means how to find the theoretical frequencies. By usual manner, it is not easy because the total sample space has 2 power 5 elements, correct? So it is not feasible. Instead of that, since it follows a binomial random variable, because n is finite, n is 5 and the probability of success is constant for each trial, that is 0.5. So I can have the probability of x success, that is here head turning up, P of x is NCX 5CX P power x, that is half power x, into Q power 5 minus x, that is half power 5 minus x. So I have the probability function here is now NCX into half power x into half power 5 minus x. Since the bases are same, I can write it as 5cx into half power x plus 5 minus x gives half power 5, that is 1 by 2 power 5. So that is 5cx by 32. Now out of 50, the expectation, so we have to multiply this by 50. So if I calculate the theoretical observation, so x turning up 0, that means the total number of heads 0, that means P of 0 is 5c1 by 32, 5 by 32 into 50, that is 1.56, very close to the observed fact. X equal to 1, that gives 5c1, 5 by 32 into 50, 7.81. Likewise, when x is 2, 5c2, that is 10 by 32 into 50, 15.63. Now when x equal to 3, phi c3, as you know, NCR is same as NCn minus r. So phi c3 is same as phi c phi minus 3, that is phi c2, which we have already calculated for x equal to 2 and x equal to 3. They are one and the same because phi c2 phi c3 are equal 15.63. Likewise phi c4 is same as phi c1, so which gives the same value 7.81, and phi c5, that is 1 by 32 into 50, that is 1.56. So if I say that the theoretical frequencies here is close to observed data, and if I draw the graph, so we can observe that the observed and the theoretical frequencies, so they are almost close. So the binomial random variable which fits into this experiment. We take problems on binomial distribution. 1. It is known that among the 10 telephone lines available in an office, the chance that any telephone is busy at an instant of time is 0.2. Find the probability that 1. Exactly 3 lines are busy. 2. What is the most probable number of busy lines and compute its probability. And 3. What is the probability that all the telephones are busy. So here clearly it follows the binomial variant as n is 10, that is finite, and let x be the probability of a telephone line busy at an instant of time, that is 0.2, that is constant for each trial, and obviously it has only two outcomes, that is either lines are busy or not busy. So it follows a binomial distribution with the probability function p of x is ncx p power x q power n minus x, where now p is the probability that any telephone is busy at an instant of time is given, that is p equal to 0.2, thereby q means 1 minus p 0.8, and n is 10 since 10 telephone lines available in an office, therefore n is 10. So I can build the probability that x telephone lines are busy at an instant of time, p of x equal to 10 cx 0.2 power x into 0.8 power 10 minus x, because p of x is ncx p power x q power n minus x. Now I can go for solving each probabilities by substituting the values of x. The first one is exactly 3 lines are busy, so that means p of 3 means we have to substitute in 10c x 0.2 power x into 0.8 power 10 minus x, where x is here 3, so that gives 10c 3.2 power 3.8 power 10 minus 3 7. So if I calculate, I get 0.2013 is the probability that exactly 3 lines are busy. The second problem, I need to find the probability that most probable number of busy lines. The most probable number of busy lines means it is nothing but the mean, which is NP. Mu is NP, where N is the total number of trials taken and P is the probability of busy lines is 0.2. So 10 into 0.2, that is 2. So that means the most probable number of busy lines is 2. Therefore the probability of this is nothing but P of 2. We substitute in 10c x 0.2 power x 0.8 power 10 minus x, which gives, by substituting x equal to 2, is 10c2 0.2 square 0.8 power 8. By calculating we get 0.3020. This is the probability of most probable number of lines busy, 0.3020. The one more problem we have is the probability that all the telephone lines are busy. So since there are 10 lines, so that means probability of all lines busy means p of 10. Substituting that, which gives now 10c 10.2 power 10 into 0.8 power 10 minus 10 is 0, so that is 1. So I have 10c 10 into 0.2 power 10, which is almost close to 0. So the probability that all telephone lines are busy is 0, means impossible events. We can say it is an impossible event. So let me take one more problem. Number 2, the chance that a bomb dropped from an airplane will strike a target is 0.4. 6 bombs are dropped from the airplane. Find the probability that 1. Exactly 2 bombs strike the target. 2. At least 1 strikes the target. 3. None of the bombs hits the target. Here also we have n equal to 6. The P is the probability that a bomb dropped from an airplane striking the target, that is given as 0.4, thereby Q is 0.6. So I can have a probability of bomb dropping from the airplane striking the target as NCX, that is 6CX into zero point 0.4 power x into zero point 0.6 power 6 minus x. So then thereby I can easily get these 3 or 4 whatever the probability is given here by substituting the corresponding values of x. So clearly here P is 0.4, Q is 0.6, N is 6. So the probability that X bombs strike the target is P of X equal to 6CX 0.4 power X into 0.6 power 6 minus X. The first problem that exactly 2 bombs strike, the probability is nothing but P of 2. Substituting X equal to 2 over here, we get 6C2 0.4 square into 0.6 power 6 minus 2 is 4. Calculating, we get 0.3110. Now the second problem is probability that at least one bomb strike the target. At least one means x greater than or equal to 1. So the probability of x greater than or equal to 1 means it is a probability from 1 to 6 we have to add. Since n is 6, so we have to start from 1, then calculate all probabilities up to 6, add it up. Instead of that, we can take the complement, so that is probability of x greater than or equal to 1 is nothing but complement of probability of x less than 1. So that means probability of x greater than or equal to 1 is 1 minus probability of x less than 1. Since it is discrete, so x less than 1 means only one integer value, that is 0. So I have 1 minus P of 0, which I can calculate, that is 1 minus P of 0 is, now substitute x equal to 0, which gives 6C0 into 0 0.6 power 6 minus 0, because here we have 0 0.4 power 0, that is 1. So 0 0.6 power 6 minus 0, that is 0 0.6 power 6. So by calculating we get 0.9533. The last one more sub question here is the probability that none of the bombs strike the target. So that means none means x equal to 0. So P of 0 is already we have taken here 6C0, same thing 0 0.6 power 6, substituting x equal to 0 over here, so which gives 0.0467. Problem number 3, find the binomial distribution which has mean 2 and variance 4 by 3. We know that for the binomial distribution, mean means mu is equal to np and variance v is equal to npq. So that means mean np is 2 and variance npq is 4 by 3. With this we can find p, q and n. So NP is 2, we substitute that here, NPQ, that gives now 2Q is equal to 4 by 3. So which means Q is equal to 4 by 3 divided by 2, that is Q is equal to 2 by 3. So P is therefore 1 minus Q, that is 1 minus 2 by 3, which is nothing but 1 by 3. Substituting P equal to 1 by 3 here, that gives N. So that means N into P, that is N into 1 by 3 is equal to 2. So N equal to 2 into 3, that is 6. So after getting total number of trial N with the probability of success P as 1 by 3 and Q as 2 by 3, we can take a binomial probability function P of x, that is NCX P power x Q power n minus x, which becomes now P of x equal to 6CX 1 by 3 power x 2 by 3 power 6 minus x. For each, now we can find the probabilities from x equal to 0 to 6, which gives the binomial distribution table. So x and P of x, when x equal to 0, P of x is 6C0, substitute over here, it gives a 6C0, 1 by 3 power 0, 2 by 3 power 6 minus 0, which is nothing but 2 by 3 power 6. Likewise, for each x up to 6, we find the value of probability function, so which gives these values. So together we can call this as a distribution table, that is binomial distribution. Problem number 4. When a coin is tossed 4 times, find the probability of getting exactly one head, at most 3 heads, at least 2 heads. So here the probability of getting head is 0.5 for each trial. So let me denote it as P. P be the probability of head turning up, then P is 0.5. So Q is the probability of getting tail, that is also 0.5. So total number of trial is N, that is 4. So I can have a probability that X heads out of 4 coins, that is probability function here is P of X equal to 4Cx 0.5 power X into 0.5 power 4 minus X. So the bases are same. So indices law, a power m into a power n, together I can say a power m plus n, so which gives 0.5 power x plus 4 minus x, that is 0.5 power 4, 1 by 2 power 4, so that is 4Cx by 16. So once we get the probability function, now I can solve the probability in each case. First one, probability of getting exactly one head, that means P of 1. So that substitute x equal to 1 here, 4C 1 by 16, 4 by 16, 0.25. Now the second problem, at most 3 heads, that means maximum is 3 heads. The probability of at most 3 head means P of x less than or equal to 3. So we have to add all the probabilities till 3, that is probability of x equal to 0, probability of x equal to 1, probability of x equal to 2, probability of x equal to 3. So I have here 4Cx by 16 is the P of x. Substitute x here. 1 by 16 is constant throughout. So 4C0 plus 4C1 plus 4C2 plus 4C3, which gives the answer 0.9375. Another way of solving this, probability of x less than or equal to 3 is the complement of probability of x greater than 3. Or we can go by this way also. So probability of x greater than 3, since n is 4, so we have only one value left out, that is x equal to 4. So 1 minus probability of x equal to 4. So that is 1 minus 1 by 16. Put x equal to 4 over here. 4C4 by 16, that is 1 by 16, which also gives the same answer, 0.9375. The last one, at least 2 heads. That means probability of x greater than or equal to 2. At least 2 or more. So I have 1 minus, I can take the complement, that is probability of x greater than or equal to 2. Otherwise 2, 3, 4 we have to take. All the probabilities we have to add. Or else we can take the complement of probability of x less than 2. Less than 2 we have only two values, that is 0 and 1. So 1 minus probability of x equal to 0 plus probability of x equal to 1, which is nothing but 1 minus, substitute over here, probability of x is 4Cx by 16. So 1 by 16 is constant. So when x equal to 0, it gives 4C0, that is 1, plus when x equal to 1, that is 4C1, that is 4. So I have to simplify this. 1 minus 5 by 16 is 0.6875. Problem number 5. 10% of the rivets produced by a machine are defective. Find the probability that out of 12 randomly chosen rivets, 1 exactly 2 will be defective, 2 at least 2 will be defective, 3 none will be defective. The 10% of the rivets are defective. So that means let P be the probability of defective rivets, which is given as 10%. That means P is 0.1. Thereby Q is 1 minus P, that is 0.9. And total number of trial N is out of 12. So that means N is 12. So probability function, that is probability that x rivets are defective, is P of x equal to NCx 12Cx P power x 0.1 power x Q power n minus x 0.9 power 12 minus x. So we can now find the probabilities given over here. 1 exactly 2 will be defective. So the probability that exactly 2 will be defective is P of 2. Substituting x equal to 2, that gives 12C2 0.1 square into 0.9 power 12 minus 2, that is 10. Simplify this, which gives 0.2301. Probability that at least 2 means minimum is 2 or more. So that is probability of x greater than or equal to 2. Now if I get in direct way, then I have to take 2 from 2 to 12. So you have to sum up all the probabilities from 2 to 12. Instead of that, we take the complement. 1 minus probability of x less than 2. So 1 minus probability of x less than 2 means we have two values left out, 0 and 1. So 1 minus probability of 0 plus probability of 1. So probability of 0 gives 0.2824. Just substitute here. That gives 12C0 1. 0.140, that is also 1. 0.9 power 12. So that is 0.2824. plus probability of 1. Substitute here x equal to 1. 12c1 0.1 power 1 into 0.9 power 11, which gives 0.3766. So the simplification provides the answer 0.3410. That is the probability that at least 2 will be defective. Now none will be defective means x equal to 0. So no defective item. So that gives here 0.9 power 12 after substituting x equal to 0. So we'll get 0.2824, which already we have taken here. Problem number 6. A die is thrown 8 times. Find the probability that 3 falls exactly 2 times, at least once, at the most 7 times. Here we want to first find the probability of getting 3 in throwing a die. So in each trial, while throwing a die, we have 6 possible outcomes, 1 to 6. In that, getting 3 is 1. So therefore, in each throw, the chance of 3 falls is 1 out of 6. That means P is 1 by 6. So Q is 1 minus P, that is 5 by 6. N, the total number of trial. So we have thrown the die 8 times, so N is 8. So the probability that 3 falls x times in 8 throw is nothing but the probability function here is P of x equal to 8cx 1 by 6 power x 5 by 6 power 8 minus x. So 1 by 6 power x and 1 by 6 power 8 minus x. So we can take the indices law here, so that gives 1 by 6 power x plus 8 minus x, that is 1 by 6 power 8. So we have P of x now is 8cx 5 power 8 minus x 6 power 8. Now I can go for each probabilities, that is probability that 3 falls exactly 2 times, that is P of 2. Substitute x equal to 8c2 5 power 8 minus 2, that is 5 power 6 by 6 power 8, which simplifies to 0.2605. Now at least once, the least is 1, so we have greater than or equal to 1. The probability that 3 falls at least 1 is P of x greater than or equal to 1. So if I go in the direct way, then I have to sum up all the probabilities starting from 1 to 8. Instead of that, we take complement of x less than 1. 1 minus probability of x less than 1 means 1 value, integer value, discrete value, that is 0. So 1 minus P of 0. So 1 minus, substitute x equal to 0, that gives 8c0 5 power 8 by 6 power 8, which simplifies to 0.7674 at the most 7 times. So that means it is less than or equal to 7. Maximum is 7. So the probability that 3 falls at the most 7 times is P of x less than or equal to 7. So if I take the probabilities, then I have to take all the probabilities up to 7, 0 to 7. Instead of that, again we take the complement, that is 1 minus probability of x greater than 7. X greater than 7 means only one value, since n is 8. So total number of trial carried is only 8. So I have 1 minus P of 8. Substitute x equal to 8 here. 8c8 5 power 8 minus 8 is 0. So left out is 8c8 by 6 power 8. So if I simplify that, it gives 0.99999405, which is almost close to 1. So that means this event is a sure event. So probability that 3 falls at most 7 times when throwing a die 8 times is almost a sure event. Next, problem number 7. In sampling, a large number of parts are manufactured by a machine. The mean number of defective in the sample of 20 is 2. Out of 1000 such samples, how many would be expected to contain at least 3 defective parts? So here, the probability of a defective, that is P, is not given directly. Instead, the mean number out of 20 is given, that is 2. So that means N is 20 and NP is 2. Mu is NP, that is given 2. With that, we can get P first. So here the random variable x is a binomial variate with mean mu is, that is NP is 2, where N is 20. So that means P is equal to 22 by 20, that is 1 by 10, which is nothing but 0.1. So hence Q is 1 minus P, that is a 0.9. So now I have N20, the probability of success, that is defective item, is 0.1 and Q is 0.9. Thereby the probability that x number of parts are defective, probability function P of x here is 20cx 0.1 power x 0.9 power 20 minus x. Now I can go for finding the probability that contain at least 3 defective parts. That means probability of x greater than or equal to 3. So if I take greater than or equal to 3, then 3 to 20, we have to add all the probabilities. So which is a huge task. Instead of that, we take the complement, 1 minus probability of x less than 3. That means 1 minus probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2. Here each I can get by using this probability function already defined over here, 20cx, 0.1 power x, 0.9 power 20 minus x, substitute x equal to 0, 1, 2. So and simplify. So which simplifies to 0.323. So we can take that by substituting x as 0, x as 1, x as 2. So now once I get the probability that at least 3 defective part is 0.323, now I want out of 1000 such samples, how many would be expected? So I have the expected number, I can multiply that by 1000. The number of samples having at least 3 defective parts out of 1000 such sample is 1000 into 0.323, that is 323. Problem number 8. In 800 families with 5 children each, how many families would be expected to have 3 boys, 5 girls, either 2 or 3 boys, and at most 2 girls by assuming probabilities of births of boys and girls to be equal? Here, the success can be taken as having a boy or girl in the family, but since we have here problem related to boys more of number, so I can take now probability P, that is having a boy in the family. So now since it is given equal priority both to boys and girls, so P, that is probability of having a boy, is half, as well as probability of having a girl, that is Q, is also half. The total number of trial N. So here since it is with 5 children each, so therefore N equal to 5. So the probability that X number of boys out of 5 children is a probability function P of X 5cx half power x into half power 5 minus x, which I can further simplify this, that is half power x plus 5 minus x, that is half power 5 means 1 by 2 power 5 is nothing but 1 by 32 times 5cx. Now here I want expected number of families out of 800 families having all these chances. So that means I want expected number of families having x number of boys in 800 families. So I need to multiply this by 800. So we have to find the expected number in respect of 800 families, means 800 times P of x is nothing but 800 into 5cx by 32, which I can simplify, which gives 25 5cx. So let me denote it as f of x. So f of x means what? So x number of boys out of 800 families. That means total number of families out of 800 families having x number of boys. So that means the first question, expected number of families with the 3 boys, means f of 3. So which gives 25 into 5c3, simplify, that gives 250. Now second one is 5 girls, means 0 boys. So expected number of families with 5 girls, that is 0 boys. So I have to calculate f of 0, that is 25 into 5c0, which is nothing but 25. The next question is expected number of families with either 2 or 3 boys. So that means either 2 means f of 2 or f of 3. That means sum of this f of 2 plus f of 3, which is 25 times 5cx is nothing but here 5c2 plus 25 times 5c3, 25 common, you can take it out, 5c2 plus 5c3, simplify, that gives 500. The last problem here is expected number of families with at most 2 girls. So that means maximum 2 girls. So means that families can have 0 girl, 1 girl or 2 girl. So in terms of boys, I can say 0 girl means 5 boys and 0 girl, or 4 boys and 1 girl, or 3 boys and 2 girls, since they have 5 children each. So together it is 5 in each case. So that means it is probability of having 5 boys or 4 boys or 3 boys. So we can find f of 5, f of 4, f of 3, add it up. So that gives the expected number of families with at most 2 girls. So we have 25 into 5c5 plus 5c4 plus 5c3, which simplifies to 400. So therefore I can say expected number of families with at most 2 girls is 400. Problem number 9. Fit a binomial distribution for the following data and obtain the expected frequencies. The data here given for x ranging up to 0 to 10 with its frequency, that is f equal to 6, 20, 28, 12, 8, 6, 0, 0, 0, 0, etc. So that means the observed frequencies are given. Now I want to find the expected frequencies by fitting this data into a binomial distribution. So that means if at all I want to fit it to a binomial distribution, I have to construct the probability function for binomial variate p of x, that is ncx p power x q power n minus x, where n is already given I want to now find probability of success P. So how I can find that? So since I know that for binomial distribution the mean is nothing but mu is equal to NP. So first let me take from this data the mean. So which I can find the mean as nothing but x bar is nothing but summation of f into x by summation f. So summation of f into x, the frequency into x. So sum of the product of these two. So I have taken that. So that is 0 into 6 plus 1 into 20, that is 20, plus 2 into 28 plus 3 into 12 plus 4 into 8 plus 5 into 6 plus everything now vanishes. So that divide by total sum of frequencies, that is here 80. So 174 by 80 gives 2.175. So that means this is the mean of the binomial distribution, which is nothing but NP. So since n is 10, so from that I can get P. So in binomial distribution we know that mu is NP, which is already obtained now, that is 2.175. Since n takes 0 to 10, so x takes the value 0 to 10, that means n equal to 10. So we can get P, that is 2.175 divided by 10, 0.2175. So once I get P, Q is nothing but complement of P, that is 1 minus P, which is 0.7825. With this we have the probability function here, P of x equal to NCX P power x Q power n minus x. Substitute, that gives 10cx 0.2175 power x 0.7825 power 10 minus x. So I can now find the probability for each x varies from 0 to 10, so which helps us to find the theoretical frequencies or expected frequencies. I just calculated over here, so that gives the binomial distribution, and the expected frequencies are given by multiplying. So I can, once I get P of x, I can get f of x, that means expected number, by multiplying this by 80. So how I got this number? First I got the probability for each by using this. So when x equal to 0, that is 10c0 0.21750 into 0.7825 power 10 minus 0. So that means P of 0 is 0.7825, that gives 0.0861. Likewise for each value, by substituting x equal to 0 to 10, I got all these data. Now if I want the expected number out of how many? Out of 80. The total frequency is 80. So I need to multiply this 80 into P of x. F of x is nothing but multiply that by 80. So that's all. So we have to multiply, F means here 80 into P of x. So which gives the expected number of frequencies or theoretical frequencies. So I got one by one by substituting. Once you get P of x, sorry, it is 80 into P of x. Once you get P of x, you can simply multiply by 80, so which gives the theoretical frequencies, that is 7, 19, 24, 18, 9, 3, 0, 0, 0, 0, 0. Correct? I hope it is clear. So if you want, you can just confirm the observed data here, observed frequency here, and this is the theoretical or expected frequencies by fitting a binomial distribution to the given data, so which almost close to the observed data. Problem number 10. 5 dice were thrown 96 times and the number of times an odd number actually turned out in the experiment is given. That means getting odd number 1 or 3 or 5, throwing 5 dice at a time, and this is taken for 96 times, and the observed frequencies are given over here. So that means, so no dice turning out to be odd number, that is 0, is only once. So one die turning out to odd number, that is 10 times. Likewise all 5 dice turning out to odd number, that is 8 times. Out of 96 times the data is given, provided. Now we have to fit a binomial distribution to this data and calculate the theoretical or expected frequencies. So in the last slide we have taken the help of mean. First we get the mean, then we got probability of success. So here, since it is simple, we can directly get the probability of getting 1 or 3 or 5 in each trial. So since there are 6 possible outcomes, throwing a die means 6 possible outcomes. So total number of outcomes are 6. Out of that, favorable to this event, that is getting odd, is 3. So that means P, I can directly take probability of getting 1 or 3 or 5 in each trial, that is 3 by 6 means 1 by 2, 0.5. So therefore Q is 1 minus P, that is also 0.5. Now total trial, that is 5 dice were thrown, so that means N equal to 5. So I can now build the probability function, that is X denote the number of times an odd number turning out. So the binomial probability distribution function P of X is NCX P power X Q power N minus X now becomes 5CX 0.5 power X 0.5 power 5 minus X, which I can simplify this 1 by 2 power 5, that is 1 by 32. So I get 5CX by 32. But here we are interested in finding the expected number of frequencies, that is expected number of dice turning out 1 or 3 or 5 out of 96. So that means we have to multiply this by 96. So which I can say 5 dice were thrown 96 times, therefore the expected frequencies were obtained from 96 times multiplied by this probability function. I denote it as f of x. So 96 into p of x is 5cx by 32, which I can simplify 96 by 32, that is 3 times 5cx. Now I want to find the theoretical frequencies or expected frequencies for each of x varying from 0 to 5. So put 1 by 1, so that gives corresponding expected frequencies. So that means when x equal to 0, 3 into 5c0, that is 3 into 1, which we get 3. When x equal to 1, 3 into 5c1, that is 3 into 5, 15, likewise. So I have calculated that 5c2 is 10, so 3 into 10, 30. So once it is done, 5c3 is same as 5c2, so that is again 3 into 10, 30. 5c4 is same as 5c1, so that is 3 into 5, 15. 5c5 is 1, so 3 into 5, sorry, 5c5 is 1, 3 into 1, that is 3. So I have the expected theoretical frequencies 3, 15, 30, 30, 15, 3. So which is for the given observed frequency is almost close, we can observe here. So thus we have taken these data and fit into a binomial distribution. So in this video I try to introduce you binomial distribution starting from Bernoulli trial and taken maximum number of problems. In the next video, we move on to the next distribution on discrete probability distribution, that is Poisson distribution. Thank you.